For 70 years, we understood how supermassive black holes formed. Stars collapsed. Small black holes merged. Over billions of years, they grew into the monsters at the hearts of galaxies. That is what every textbook told us. That is what every physicist believed. But the James Webb Space Telescope just shattered that certainty. It found supermassive black holes in the early universe. Black holes that weigh tens of millions of times more than our Sun. Black holes that existed when the universe was barely 700 million years old. The math does not work. The timeline is impossible. These black holes had no time to exist. And yet, there they are, staring back at us through 13 billion years of cosmic history, demanding that we rewrite everything we thought we knew about the birth of the universe. If you want to discover the truth about the impossible monsters lurking at cosmic dawn, hit that like button and subscribe. Brace yourselves. The revelation begins. The James Webb Space Telescope was designed to see the impossible. It peers back to the edge of time itself, to the first billion years after the Big Bang, to an era astronomers call cosmic dawn. And what it found there broke physics. Tiny red dots, compact galaxies glowing faintly in infrared light. Scientists call them little red dots. Each one harbors a secret. At their centers sit supermassive black holes, monsters weighing 50 million times the mass of the Sun, black holes that should not exist yet. The universe at that time was only 700 to 1.5 billion years old. That is 1/20th of its current age. Imagine a toddler with the body of a heavyweight champion. That is what Webb found. Black holes so massive, so impossibly developed, that every model of black hole formation screamed in protest. One discovery stands above the rest. Astronomers found a supermassive black hole called QS01. It sits naked in space, completely alone. No galaxy surrounds it. No stars orbit it. Just a monstrous black hole, 50 million solar masses, floating in the void like a cosmic orphan. It exists just 750 million years after the Big Bang. That is impossible. A black hole that massive should be at the center of a giant galaxy. It should have taken billions of years to form. But there it is, fully formed, utterly alone, defying every law we thought governed the universe. The crisis is mathematical. Black holes grow by consuming matter. They feed on gas, dust, and stars. But there is a limit to how fast they can eat. Physics imposes a speed limit on cosmic gluttony. When a black hole feeds, the infalling matter heats up and radiates energy outward. That radiation creates pressure. That pressure pushes matter away. This is called the Eddington limit. It is nature's brake pedal on black hole growth. Even if a black hole gorges itself at the maximum possible rate, feeding continuously without pause, it takes hundreds of millions of years to grow from stellar mass to supermassive scales. The black holes Webb found did not have that time. They formed too fast. They grew too large. The universe was too young. Science is brutal when confronted with the impossible. It demands answers. For decades, the standard model held firm. Supermassive black holes formed from light seeds. A massive star dies in a supernova. Its core collapses into a black hole. That black hole weighs maybe 10 to 100 times the mass of the Sun. It begins to feed. Over millions of years, it merges with other black holes. It consumes gas clouds. Slowly, painfully slowly, it grows. After 1 billion years, maybe 2 billion, it reaches supermassive status. That is the theory. That is what we taught in every classroom. But Webb just proved it wrong. The telescopes do not lie. Astronomers led by Anthony Taylor confirmed the oldest known supermassive black hole in August 2025. It sits in a galaxy called Kuiper's LRDZ9. The black hole formed just 500 million years after the Big Bang. This is about as far back as you can practically go, Taylor said. But it is not just one anomaly. Webb found dozens, each one a cosmic impossibility, each one a nail in the coffin of the old theory. Then came the mergers. In July 2024, Webb detected two supermassive black holes locked in a death spiral. The system is called Z7. It exists 740 million years after the Big Bang. One of the black holes weighs 50 million solar masses. The other weighs slightly less. They orbit each other, spiraling inward, destined to collide. This is the most distant black hole merger ever detected, and it raises a terrifying question. If black holes were already merging at cosmic dawn, how did they get that massive in the first place? The physics does not add up. The timelines do not work. The universe was too young, too small, too empty to build these monsters through conventional means. Something else happened. Something we missed. Some mechanism we never considered. The old model is dead. The light seed theory collapsed under the weight of Webb's observations. And now scientists are proposing ideas so radical, so strange, that they sound like science fiction. What they discovered next was even stranger. The James Webb Space Telescope sees what human eyes cannot. It operates in infrared. It captures light that has traveled for 13 billion years. Light stretched by the expansion of the universe. Light from the cosmic dawn. When astronomers pointed Webb at the earliest epochs of cosmic history, they expected to find faint, distant galaxies. What they found instead rewrote the textbooks. Little red dots. That is what scientists call them. Compact sources of light, glowing crimson in Webb's infrared vision. They are small. They are bright. And they are everywhere in the early universe. At first, astronomers thought they were looking at distant galaxies. But the spectroscopy revealed something shocking. These were not galaxies in the traditional sense. They were active galactic nuclei, supermassive black holes feeding voraciously, outshining entire galaxies from the centers of impossibly young cosmic structures. The data was undeniable. Each little red dot harbored a black hole weighing millions, sometimes tens of millions, of solar masses. And they existed between 700 million and 1.5 billion years after the Big Bang. That is the cosmic equivalent of finding a skyscraper in a construction zone where the foundation was poured yesterday. The universe had barely begun. Stars were just starting to form. Galaxies were in their infancy. And yet, there they were, fully formed monsters, impossible giants. But one object defied every expectation. Astronomers Peter van Dokkum and Gabriel Brammer were not looking for it. They were studying a distant galaxy merger. Two galaxies colliding in the early universe. Routine observation, standard science. Then they saw the third object, a supermassive black hole sitting between the two galaxies, not inside either one, just floating there, alone, naked. They named it QS01. It weighs 50 million times the mass of the Sun. It exists 750 million years after the Big Bang, and it has no home. No galaxy surrounds it, no stellar halo, no dust disk, just a black hole, impossibly massive, impossibly isolated, impossibly young. We were stunned, Van Dokkum said. This was not supposed to exist. Every model of black hole formation requires a galaxy. Black holes form from stars. stars forming galaxies. Without a galaxy, there should be no black hole. And yet, there it sat. A cosmic orphan. A monster without a birthplace. The discovery sent shockwaves through the astronomical community. QS01 was not just an anomaly. It was proof that something fundamental was missing from our understanding of the early universe. How does a 50 million solar mass black hole form in isolation? Where did it come from? What created it? Think of it this way. Imagine finding a fully grown adult human, alone in the wilderness, with no parents, no family, no village anywhere nearby. That is QS01, a cosmic impossibility, an object that should not exist, and yet does. Webb found more. In July 2024, the telescope detected the most distant black hole merger ever observed. The system is called JWST, two supermassive black holes locked in a gravitational dance, spiraling toward each other at 740 million years after the Big Bang. One weighs 50 million solar masses. The other is slightly smaller. They will collide. When they do, they will release gravitational waves so powerful that they will ripple through the fabric of space-time itself. But the merger raises more questions than it answers. If these black holes were already massive enough to merge at cosmic dawn, how did they form? The light seed model says black holes grow slowly. They take billions of years to reach supermassive scales. But JWST proves that timeline is wrong. These black holes were already giants when the universe was an infant. Then there is Kuiper's LRD Z9. Anthony Taylor and his team announced the discovery in August 2025. It is the oldest confirmed supermassive black hole ever found. It formed just 500 million years after the Big Bang. That is 150 million years younger than the universe at the time of the previous record holder. This is about as far back as you can practically go, Taylor said. The black hole is actively feeding, consuming gas and dust, glowing brightly in X-rays and infrared. It should not be there. The universe was too young. The timeline does not allow it. Webb's observations are consistent. Supermassive black holes are common in the early universe. They are not rare anomalies. They are everywhere. And every single one of them violates the standard model of black hole formation. The light seed theory is dead. The old timeline is broken. Physics is screaming at us to find a new explanation. The universe is revealing its secrets, one impossible observation at a time. These black holes are not outliers. They are not measurement errors. They are real. They are massive. They are ancient. And they are forcing us to confront a terrifying truth. We do not understand how the universe began. We do not understand how structure formed in the first billion years. We thought we did, but Webb just proved us wrong. This solved one problem, but it created an even bigger mystery. If the standard model is wrong, what is the right answer? How did these black holes form so fast? And why did no one see this coming? Time is the universe's ultimate constraint. Nothing escapes it. Not stars, not galaxies, not even black holes. Every cosmic structure needs time to grow, time to accumulate mass, time to evolve, time to become what it is destined to be. And the supermassive black holes Webb found did not have that time. The math is brutal. It does not lie. It does not bend. And it absolutely does not care about what we observe. The equations governing black hole growth have been understood for decades. They are simple. They are elegant. And they are utterly unforgiving. Start with a stellar mass black hole. 10 solar masses, maybe 100 if you are lucky. That is what you get when a massive star collapses. The star dies in a supernova. The core implodes. Gravity wins. A black hole is born. So far, so good. This happens all the time in the universe. We have observed it. We understand it. No controversy here. Now comes the hard part. That tiny black hole needs to grow. It needs to consume matter, gas, dust, stars, other black holes, anything within reach of its gravitational pull. And it needs to do this for a very, very long time. How long? Try hundreds of millions of years, maybe a billion. That is how long it takes to go from stellar mass to supermassive scales using conventional physics. But there is a problem. Physics imposes a speed limit. It is called the Eddington limit, and it is nature's way of saying slow down. Here is how it works. When a black hole feeds, matter spirals inward. As it falls, it accelerates. It heats up. Friction generates temperatures of millions of degrees. That superheated matter radiates energy. Light, X-rays, intense radiation blasting outward in all directions. And that radiation creates pressure, outward pressure, pressure that pushes matter away from the black hole, the same matter the black hole is trying to consume. Think of it like this. Imagine trying to drink from a fire hose. The harder you suck, the more water sprays in your face. That is the Eddington limit. The faster a black hole feeds, the more it radiates, and the more it pushes food away from itself. There is a maximum feeding rate, a cosmic speed limit on gluttony. No black hole can exceed it for long without blowing away its own food supply. The numbers are unforgiving. Even if a black hole feeds at the absolute maximum rate, continuously, without pause, without ever running out of gas, it can only double its mass every 50 million years or so. That is the Eddington limited growth rate. Start with a 100 solar mass black hole. Feed it perfectly for 50 million years. You get a 200 solar mass black hole. Feed it for another 50 million years. 400 solar masses. Keep going. After 500 million years of perfect continuous feeding, you might reach 100,000 solar masses. After a billion years, maybe 10 million solar masses. But the black holes Webb found weigh 50 million solar masses. And they formed in less than 750 million years. Some formed in just 500 million years. Do the math. It does not work. The timeline is too short. The growth rate is too fast. Even if these black holes started as massive seeds, even if they fed continuously at maximum capacity from the moment the universe began, they still should not exist yet. The problem gets worse. Black holes do not feed continuously. They have quiet periods, phases where the gas supply runs out, moments where stellar winds or supernova explosions blow away the infalling matter. Real black holes grow in fits and starts, not smooth exponential curves. That makes the timeline even tighter, even more impossible. Scientists tried to fudge the numbers. Maybe black holes can exceed the Eddington limit temporarily. Super Eddington accretion, feeding at 10 times, 100 times the theoretical maximum. It is possible. We have seen hints of it in some active galactic nuclei. But even super Eddington feeding cannot explain what Webb found. You would need black holes feeding at impossible rates for impossible durations with impossible efficiency. Every variable maxed out. Every constraint violated. And even then, the math barely works. QSO-1 is the poster child for this crisis. 50 million solar masses, 750 million years after the Big Bang. No galaxy, no visible fuel source, just a naked black hole floating in space, impossibly massive. If it formed from a stellar mass seed, it would have needed to feed at more than 100 times the Eddington limit, continuously, without pause, from the moment the first stars formed. That is not physics, that is fantasy. Kepler's LRD Xenine is even worse. 500 million years after the Big Bang. That gives the black hole even less time to grow. The universe at that point was barely old enough for the first generation of stars to live and die. Where did the seed come from? How did it grow so fast? The standard model has no answer. The crisis is existential. The old theory is dead. Stellar mass seeds cannot grow fast enough. The Eddington limit is too restrictive. The timeline is too short, and the observations keep piling up. Webb is finding more supermassive black holes in the early universe every month. Each one an impossibility. Each one a violation of the laws we thought governed cosmic evolution. Physics is screaming at us. The universe is telling us we missed something fundamental. Some mechanism we never considered. Some process that can build supermassive black holes in a fraction of the time the standard model requires. And that question leads us directly to the seeds. If light seeds cannot grow fast enough, maybe the universe started with something heavier. For 7 decades, scientists had a story. It was elegant, it was logical, it explained everything. Supermassive black holes formed from light seeds, small black holes born from dying stars. Over billions of years, through patient accumulation and cosmic collisions, they grew into the monsters we see today. That was the theory. That was what every textbook taught. That was the foundation of modern astrophysics. And it was wrong. The light seed theory starts with stars. Massive stars. Giants weighing 50, 100, 200 times the mass of the Sun. These are rare beasts, short-lived, burning through their nuclear fuel in just a few million years. When they die violently. Core collapse supernovae. Explosions so bright they outshine entire galaxies for weeks. And at the center of each explosion, a black hole is born. These are stellar mass black holes. Small by cosmic standards. 10 solar masses, maybe 30. In rare cases, up to 100 solar masses, but never more. The physics of stellar collapse limits how massive they can be. Most of the star's mass gets blown away in the supernova. Only the core collapses. That is your seed. A tiny black hole adrift in space, hungry and ready to grow. Now the waiting begins. The black hole needs food, gas clouds, stray stars, anything it can gravitationally capture. But space is vast. Matter is sparse. Most black holes wander through the cosmos, barely growing at all. They are cosmic hermits, isolated, starving, gaining maybe a few solar masses every million years, unless they get lucky, unless they find themselves in a rich environment, the center of a star cluster, the core of a forming galaxy, a region dense with gas and dust. There, the black hole can feed. There, it can grow, slowly, painfully slowly, constrained by the Eddington limit, doubling its mass every 50 million years if conditions are perfect. But growth through feeding is only half the story. Black holes also grow through mergers. 2 black holes meet. Gravity binds them together. They spiral inward. Eventually, they collide. The merger happens in a fraction of a second. The gravitational waves released can be detected across the universe. And the result is a single, larger black hole. This is how the light seed theory builds supermassive black holes. Merger after merger, generation after generation. 100 solar mass black hole merges with another 100 solar mass black hole. You get 200 solar masses. That black hole feeds for 100 million years, doubling to 400 solar masses. It merges again, 800 solar masses. Feed, merge, over and over. 1 billion years pass, maybe 2 billion. Finally, you reach supermassive scales. 10 million solar masses, 100 million, 1 billion. The theory worked beautifully for the modern universe. We see supermassive black holes at the centers of most galaxies today. Our own Milky Way harbors one, Sagittarius A star, 4 million solar masses. It formed over billions of years, exactly as the light seed model predicts. The same is true for Andromeda, for M87, for every major galaxy in the local universe. Their supermassive black holes are ancient. They grew slowly. They followed the rules. But the early universe is not the modern universe. The rules are different there. The timeline is compressed, and the light seed theory collapses under the weight of Webb's observations. Here is the fatal flaw. The first stars did not form immediately after the Big Bang. There was a dark age, a period of hundreds of millions of years when the universe was too hot, too uniform, too empty to form stars. Hydrogen and helium gas filled space, but it had not yet collapsed into dense clouds. No stars, no galaxies, just a vast, expanding void. The first stars finally ignited around 200 million years after the Big Bang, maybe 300 million years. These were population 3 stars, giants made of pure hydrogen and helium. No heavy elements, no metals. They burned bright and died fast. When they collapsed, they formed the first stellar mass black holes. Now do the math. Kuiper's LRD Z9 exists 500 million years after the Big Bang. The first stars formed at 200 million years. That gives the supermassive black hole at the center of Kuiper's LRD Z9 exactly 300 million years to grow from a stellar mass seed to supermassive scales. 300 million years. That is 6 Eddington doubling times. Start with 100 solar masses. Double 6 times. You get 6,400 solar masses. Not even close to supermassive. QSO-1 is worse. 750 million years after the Big Bang. 50 million solar masses. That would require 10 Eddington doubling times. Starting from 100 solar masses, feeding continuously at the absolute maximum rate, you could theoretically reach 100 and 2,400 solar masses. Still not enough, not even close. And remember, these calculations assume perfect conditions. Continuous feeding, no interruptions, no periods of starvation, no gas depletion. Every variable optimized. In reality, black holes do not grow that smoothly. They have quiet periods, feeding frenzies followed by long droughts. The real growth rate is much slower than the theoretical maximum. The light seed theory is dead. It cannot explain Webb's observations. The timeline is too short. The growth rate is too fast. No amount of super Eddington feeding can bridge the gap. No number of mergers can build 50 million solar mass black holes in 750 million years, starting from stellar remnants. Scientists clung to the theory for as long as they could. They tweaked the parameters. They proposed exotic feeding mechanisms. They suggested that maybe, just maybe, the early universe was different enough to allow faster growth. But the observations kept coming. More supermassive black holes at cosmic dawn. More impossibilities. More violations of the fundamental laws. The evidence is overwhelming. Light seeds do not work. The old model is broken, and the universe is demanding a new explanation. But what they discovered next changed everything. A galaxy caught in the act of creation. A cosmic collision that revealed the birth of a monster. Some discoveries happen by accident. Scientists point their telescopes at one thing and find something entirely different. Something unexpected. Something that rewrites the rules. That is exactly what happened to Peter van Dokkum and Gabriel Brammer. They were not looking for the impossible. They were studying a routine galaxy merger in the early universe. Just another pair of colliding galaxies, standard cosmology, nothing special. And then they saw the third object. It was 2024. Webb had been operational for 2 years. The data was pouring in. Van Dokkum and Brammer were analyzing images of distant galaxies, cataloging structures, measuring redshifts. They found a pair of galaxies locked in a gravitational dance. 2 young galaxies colliding in the cosmic dawn. This happens all the time. Galaxy mergers are common in the early universe. They are how large galaxies form. Nothing unusual. But something in the image caught their attention. A third point of light, sitting right between the 2 galaxies, not inside either one, just floating there, in the space between, glowing brightly in infrared, too bright to be a star, too compact to be a galaxy. They ran the spectroscopy. The results came back, and Van Dokkum could not believe what he was seeing. A supermassive black hole, 50 million solar masses, floating in intergalactic space, completely isolated, no host galaxy, no stellar envelope, no accretion disk, just a naked black hole, sitting in the void like a cosmic orphan. "We were stunned," Van Dokkum said. This violated everything they knew about black hole formation. They named it QSO-1, but the press had a better name, the lonely black hole. Some called it the orphan, others dubbed it the rogue, but the scientific community settled on a different term, the direct collapse candidate. Because if this black hole truly formed in isolation, if it truly has no galaxy, then it could not have formed from stars. It must have formed some other way. The discovery was revolutionary. For decades, every supermassive black hole ever observed sat at the center of a galaxy. That was the rule. Black holes and galaxies grow together. They co-evolve. The black hole feeds on gas from the galaxy. The galaxy's gravity keeps the black hole anchored at its core. You cannot have one without the other. Or so we thought. QSO-1 broke that rule. Here was a supermassive black hole with no galaxy, no visible birthplace, no obvious formation mechanism. It existed 750 million years after the Big Bang, in an era when galaxies were just beginning to form. And it was fully grown. 50 million solar masses, massive enough to anchor a large galaxy, but it had no galaxy to anchor. The 2 colliding galaxies nearby offered a clue. Van Dokkum and Brammer realized they were witnessing something extraordinary. Not just a merger, not just an isolated black hole, but potentially the birth of a supermassive black hole. The collision itself might have created QSO-1. Here is how it could work. 2 galaxies collide. Their gas clouds smash together at hundreds of kilometers per second. The collision compresses the gas. Pressure builds. Temperature rises. Normally, this triggers star formation. The compressed gas fragments into dense clumps. Each clump collapses into a star. You get a starburst galaxy. Millions of new stars born in a cosmic frenzy. But under the right conditions, something else can happen. If the gas cloud is massive enough, dense enough, and hot enough, it might not fragment. It might collapse as a whole. All at once. No stars, no intermediate steps. Just a direct collapse into a black hole. A heavy seed. Tens of thousands of solar masses. Maybe hundreds of thousands. Born in an instant. This is called direct collapse. It is a theory that has existed for decades. Scientists proposed it as a solution to the supermassive black hole timeline problem. If you start with a heavy seed instead of a light seed, you cut the growth time dramatically. A 100,000 solar mass black hole only needs 7 Eddington doubling times to reach 50 million solar masses. That is 350 million years. Still tight, but mathematically possible. But direct collapse was always theoretical. No one had ever seen it happen. No one had ever found a black hole caught in the act of forming this way. The conditions required are extreme. The gas must be pristine. No heavy elements, no metals. Even a tiny amount of contamination causes the gas to cool and fragment into stars instead of collapsing directly. The early universe was the only place this could happen. Before the first generation of stars polluted the cosmos with heavy elements. And now, Webb may have found the smoking gun. QS01 sits right between 2 colliding galaxies. The timing is perfect. The location is perfect. The mass is perfect. This could be a direct collapse black hole, formed not from stars, but from the collision itself. A heavy seed, born massive, skipping the entire stellar phase. NASA confirmed the discovery in July 2025. They called it the possible direct collapse black hole. The language was cautious. Scientists do not like to claim victory prematurely. But the excitement was palpable. If QS01 is truly a direct collapse object, it proves the theory. It shows that heavy seeds can form. It provides a mechanism for building supermassive black holes in the early universe. But there is a twist. QS01 is not inside a galaxy. It is floating in the space between galaxies. That raises a troubling question. If it formed from the collision, why is it not bound to either galaxy? Did the collision eject it? Is it a cosmic cannonball shot into intergalactic space by the violence of the merger? Or did it form in isolation, in a rare pocket of pristine gas between the galaxies? Van Dockum and Brammer are still analyzing the data. They are measuring the black hole's velocity. They are studying the gas dynamics around it. They are trying to piece together its origin story. But one thing is certain. QS01 is not an anomaly. It is not a measurement error. It is real. It is massive. And it is forcing scientists to reconsider everything they thought they knew about black hole formation. The discovery opened a door. If heavy seeds can form through direct collapse, if galaxy mergers can create supermassive black holes in a single event, then the timeline problem is solved. You do not need billions of years. You do not need endless mergers and slow accretion. You just need the right conditions. A massive gas cloud, a violent collision, and gravity does the rest. This solved one mystery, but it raised an even bigger question. If direct collapse can happen, how common is it? And could there be an even more exotic explanation for the supermassive black holes Webb found? Direct collapse is nature's shortcut. It bypasses the slow grind of stellar evolution. It skips the merger lottery. It takes a massive cloud of gas and crushes it into a supermassive black hole in one catastrophic event. No stars, no intermediate steps, just raw gravitational collapse, and it might be the answer to the impossible black holes Webb found. The theory is elegant. It solves the timeline problem. Instead of starting with a 10 solar mass seed and waiting billions of years for it to grow, you start with 100,000 solar mass seed, maybe 1 million, born massive, fully formed in the cosmic dawn. From there, reaching 50 million solar masses is straightforward. 7 Eddington doubling times, 350 million years. The math works, the timeline fits. Physics stops screaming, but the conditions required are extreme. You cannot just collapse any gas cloud into a black hole. Normal molecular clouds fragment. They break apart into smaller clumps. Each clump becomes a star. That is how star formation works. Fragmentation is the default. To prevent it, to force a cloud to collapse as a whole, you need very specific conditions. First, the gas must be pristine. Pure hydrogen and helium. No heavy elements, no metals. Even trace amounts of carbon, oxygen, or iron ruin everything. Heavy elements act as coolants. They radiate energy. They lower the gas temperature. Cool gas fragments easily. Hot gas resists fragmentation. For direct collapse to work, the gas must stay hot, above 10,000 degrees Kelvin. That is only possible if the gas is metal-free. Second, you need intense radiation, ultraviolet light, bathing the gas cloud, ionizing the hydrogen atoms, keeping the temperature high. This radiation must come from nearby sources, quasars. Active galactic nuclei, the first generation of massive stars. Without this external radiation field, the gas cools and fragments. Third, the cloud must be massive, at least 100,000 solar masses, preferably more. 1 million solar masses is ideal. The sheer mass creates enormous gravitational pressure, enough to overcome the gas pressure, enough to trigger runaway collapse. Fourth, the collapse must be fast. Once it starts, it must proceed quickly. Any delay gives the gas time to cool, time to fragment, time to form stars instead of a black hole. The entire process takes maybe 100,000 years. In cosmic terms, that is an eye blink. One moment you have a gas cloud, the next moment, a supermassive black hole. These conditions are rare, vanishingly rare. They can only exist in the early universe, before the first supernovae polluted the cosmos with heavy elements, before metal-rich gas became the norm. In the first billion years after the Big Bang, pristine gas was common. Intense radiation fields existed near the first quasars and star-forming regions. Massive gas clouds were abundant. The early universe was a factory for direct collapse black holes, but proving it was always the problem. No one had ever caught one forming. Direct collapse was a theoretical solution to a theoretical problem. Until QS01. The evidence is circumstantial but compelling. QS01 sits between 2 colliding galaxies. The collision would have compressed enormous amounts of gas. The early universe had pristine gas. The nearby galaxies were forming stars, producing intense ultraviolet radiation. Every condition for direct collapse was met. And the result is a 50 million solar mass black hole with no visible host galaxy. No stars around it, no stellar population, just the black hole itself. That fits the direct collapse scenario perfectly. If QS01 formed from a collapsing gas cloud, it would not have stars. Stars only form if the gas fragments. Direct collapse prevents fragmentation. The entire cloud becomes a black hole. Nothing is left to form stars. You get a naked black hole, an orphan. exactly what Webb observed. NASA's announcement in July 2025 was cautious but significant. They called QS01 a possible direct collapse black hole. The language reflected scientific uncertainty, but the implications were clear. If this interpretation is correct, if QS01 really is a direct collapse object, then the theory is proven. Heavy seeds exist. They form in the early universe. They provide the massive starting point needed to build supermassive black holes on compressed timelines. And QS01 might not be alone. Webb has found dozens of supermassive black holes in the early universe. Many of them show similar properties: compact, extremely luminous, surrounded by minimal stellar mass. These could all be direct collapse black holes, heavy seeds scattered throughout the cosmic dawn, each one a shortcut to supermassive scales. The theory also explains the mergers Webb detected. The ZS7 system contains two supermassive black holes spiraling toward collision. One weighs 50 million solar masses. If both started as direct collapse seeds, they would have had enough time to grow to those masses through normal accretion. Start with a 100,000 solar mass seed. Feed it at the Eddington limit for 700 million years. You reach tens of millions of solar masses easily. Then the two black holes meet. Gravity binds them. They merge. 100 million solar mass monster is born. Direct collapse solves the problem. It provides heavy seeds. It cuts the required growth time by a factor of 10. It makes the impossible possible. The supermassive black holes Webb found no longer violate the laws of physics. They just require a different formation mechanism, one that only operates in the pristine conditions of the early universe. But scientists are not satisfied. Direct collapse explains some of the observations, maybe even most of them, but it does not explain everything. Kepler's LRDZ9 exists just 500 million years after the Big Bang. That is barely enough time for direct collapse seeds to grow, even under ideal conditions. And some of the little red dots show properties that do not fit the direct collapse model. The data suggests something more radical might be happening, something that predates stars altogether, something born not from collapsing gas clouds in the early universe, but from the Big Bang itself. A decades-old theory is making a comeback, a theory proposed by one of the greatest minds in physics, a theory so exotic, so strange, that most scientists dismissed it as speculation, until now. Stephen Hawking might have been right all along. The supermassive black holes Webb found might not have formed from stars, or gas clouds, or any conventional process. They might be older than galaxies, older than stars, older than atoms themselves. They might be primordial. Stephen Hawking proposed it in 1974. Primordial black holes that formed not from stars, not from collapsing gas clouds, but from the Big Bang itself. In the first fraction of a second after the universe began, when space was a seething cauldron of energy and matter, quantum fluctuations could have created pockets of extreme density, regions where matter was compressed so tightly that gravity overwhelmed everything else. Those pockets collapsed instantly. Black holes formed, not from stellar death, not from cosmic evolution, but from the violent birth of reality itself. The theory was brilliant. It was radical, and most physicists ignored it. Why? Because there was no evidence, no observations, no way to test it. Primordial black holes were mathematical curiosities. Interesting on paper, irrelevant in practice. Or so everyone thought. 50 years passed. Hawking died in 2018. his theory remained unproven, a footnote in cosmology textbooks, a what-if scenario for graduate students to debate over coffee, until the James Webb Space Telescope changed everything. The supermassive black holes Webb found are too old, too massive, too abundant. Direct collapse helps, but it does not explain all of them. Some exist too early, some grew too fast, some appear in environments where direct collapse should be impossible. The observations are pushing scientists toward more exotic explanations, and the most exotic explanation of all is primordial black holes. Here is how it works. The universe begins, not smoothly, not uniformly, but chaotically. The Big Bang was not a gentle expansion. It was a violent, turbulent explosion of space-time. In the first microseconds, the universe was unimaginably hot and dense, hotter than the core of any star, denser than the heart of any black hole today, and it was lumpy. Quantum mechanics guarantees lumpiness. At the smallest scales, reality is probabilistic. Energy fluctuates. Density fluctuates. Most fluctuations are tiny, insignificant. They smooth out as the universe expands. But some fluctuations are extreme. Rare statistical outliers. Regions where density spikes to impossible values. And in those rare pockets, gravity takes over. The pocket collapses. Instantly. There is no time for pressure to build. No time for matter to escape. The density is too high. Gravity is too strong. A black hole forms. Not from a star, not from gas. From pure energy. From the fabric of space-time itself. These are primordial black holes. They can have any mass. Small ones, large ones, microscopic ones weighing less than a gram, supermassive ones weighing millions of solar masses. It depends entirely on the size of the density fluctuation that created them. And here is the critical point. If a large enough fluctuation occurred in the first microseconds after the Big Bang, it could have created a supermassive black hole directly. No stellar evolution required. No gas cloud collapse. Just an instant transition from energy to black hole. Hawking calculated the physics. The math was sound. Primordial black holes were possible. But were they real? That was the question no one could answer. Until Webb started finding supermassive black holes that had no business existing. Kepler's LRDZ9 exist 500 million years after the Big Bang. That is barely enough time for the first stars to form and die. Nowhere near enough time for a stellar mass black hole to grow to supermassive scales. Even direct collapse struggles to explain it. But if Kepler's LRDZ9 harbors a primordial black hole, the timeline problem vanishes. The black hole did not need to grow. It was born massive, fully formed in the first moments of the universe. It just sat there for 500 million years, waiting for gas and stars to form around it. The same logic applies to QS01, a naked black hole with 50 million solar masses and no host galaxy. Direct collapse is one explanation, but primordial black holes offer another. What if QS01 formed in the Big Bang? What if it predates stars, galaxies, even atoms? It would have no stellar birthplace, no galaxy to anchor it, just a black hole, ancient beyond measure, floating through the cosmos like a cosmic fossil from the first moment of time. The theory explains more than just early supermassive black holes. Primordial black holes could be dark matter. For decades, physicists have searched for dark matter particles, exotic subatomic particles that interact only through gravity. They have built detectors deep underground. They have searched for years. They have found nothing. What if dark matter is not particles? What if it is black holes? primordial black holes scattered throughout the universe, invisible, undetectable except through their gravitational influence. It fits the observations. Dark matter behaves like it is made of massive, slow-moving objects. Exactly like black holes, dark matter does not interact with light. Neither do black holes. Dark matter clusters around galaxies. So would primordial black holes. The theory solves two problems at once. It explains the supermassive black holes in the early universe, and it explains dark matter. Scientists are taking the idea seriously. Papers are being published. Models are being refined. Observational campaigns are being planned. Webb's discoveries have breathed new life into Hawking's 50-year-old theory. It is no longer a curiosity. It is a viable explanation for some of the most profound mysteries in cosmology. But proving it is difficult. Primordial black holes look exactly like black holes formed through other mechanisms. They have the same mass, the same gravity, the same event horizon. There is no label that says, "I formed in the Big Bang." To distinguish them, scientists need indirect evidence, statistical arguments, population studies. If Webb keeps finding supermassive black holes in environments where conventional formation is impossible, the case for primordial black holes strengthens. And the observations keep coming. Every month, Webb finds more ancient black holes, more impossibilities, more violations of the conventional timeline. Each discovery is another piece of evidence that something exotic happened in the early universe, something we are only now beginning to understand. Hawking proposed primordial black holes as a theoretical possibility, a mathematical consequence of quantum fluctuations in the Big Bang. He never lived to see them discovered. But 50 years later, the James Webb Space Telescope might be proving him right. The supermassive black holes at cosmic dawn might not have grown from stars. They might not have formed from collapsing gas clouds. They might be older than everything. Relics from the first microseconds of existence. Fossils from the birth of reality itself. But the observations revealed something even stranger. A record-breaking discovery that pushed the boundaries of what Webb could see. The oldest supermassive black hole ever found. And it was not alone. August 2025. Anthony Taylor made an announcement. His team had found something extraordinary. The oldest confirmed supermassive black hole in the universe. Not a candidate, not a maybe. Confirmed. Spectroscopically verified. Undeniable. And it existed just 500 million years after the Big Bang. The galaxy is called Kuiper's LRD Z9. The name is technical, unmemorable, but the discovery is anything but. This black hole sits at the edge of what Webb can observe. It is so distant that its light has traveled for over 13 billion years to reach us. We are seeing it as it was when the universe was barely 3% of its current age, a cosmic infant, and at its center burns a supermassive black hole that should not exist yet. This is about as far back as you can practically go, Taylor said. He was not exaggerating. Kuiper's LRD Z9 pushes Webb to its absolute limits. Any earlier and the light becomes too faint to analyze. Any more distant and the spectroscopy becomes too uncertain. This is the edge, the boundary. The earliest epoch where we can confirm what we are seeing. And what we are seeing is impossible. 500 million years after the Big Bang. That is the timeline. The universe had barely cooled. The first stars were just igniting. Population 3 giants, massive and short-lived, burning through their fuel in a few million years. Some had already died. Some had collapsed into stellar mass black holes, but there had not been enough time for those black holes to grow. Not through conventional means, not from light seeds. The math is unforgiving. The first stars formed around 200 million years after the Big Bang, maybe 250 million. That gives the black hole in Kuiper's LRDZ9 at most 250 million years to grow from a stellar remnant to supermassive scales. 250 million years. That is 5 Eddington doubling times. Start with 100 solar masses. Feed continuously at maximum capacity. You reach 3,200 solar masses, not even close to supermassive. But Kuiper's LRDZ9 is not a 3,000 solar mass black hole. It is orders of magnitude larger. The exact mass is still being calculated, but preliminary estimates suggest millions of solar masses, maybe tens of millions, fully supermassive. Fully impossible. Taylor's team used every tool at their disposal. Webb's near-infrared spectrograph, the MIRI instrument, X-ray observations from Chandra. They analyzed the light spectrum. They measured the redshift. They calculated the luminosity. Every data point confirmed what they were seeing. A supermassive black hole actively feeding in the cosmic dawn, devouring gas and dust, glowing brightly in X-rays and infrared, a monster that had no business existing yet. The discovery broke the previous record by 150 million years. That might not sound like much, but in the early universe, 150 million years is everything. It is the difference between possible and impossible. It is the difference between physics working and physics breaking. Every million years you push back makes the timeline tighter. Every million years makes conventional formation mechanisms less plausible. And Kuiper's LRDZ9 might not even be the oldest. Taylor was careful with his language. This is about as far back as you can practically go, he said. Practically, not theoretically. Not absolutely. Practically. Webb is pushing against instrumental limits. The telescope can see farther, but confirming what it sees becomes increasingly difficult. The light is too faint. The spectral lines are too weak. The uncertainty too high. There could be older black holes out there. Ones Webb has glimpsed, but cannot yet confirm. Little red dots at even higher redshifts. Faint smudges at the very edge of detection, each one potentially another supermassive black hole from the cosmic dawn. Each one another impossibility waiting to be verified. The implications are staggering. If supermassive black holes existed just 500 million years after the Big Bang, they were among the first structures to form in the universe, before large galaxies, before galactic clusters, before most stars. Black holes came first. That inverts our understanding of cosmic evolution. We thought galaxies formed first and black holes grew inside them. But Kuiper's LRDZ9 suggests it might be the other way around. Black holes form first. Galaxies assembled around them. Think of it this way. We believed black holes were passengers, hitchhikers riding along in galaxies, growing slowly over billions of years. But the observations suggest they were drivers, architects, the first massive objects to condense out of the primordial soup, seeds around which everything else organized, gravity wells so deep that gas and stars fell into orbit around them. Galaxies did not make black holes. Black holes made galaxies. This is a fundamental shift, a Copernican revolution in cosmology. Everything we thought we understood about structure formation is being rewritten. Black holes are not endpoints. they are beginnings. And Taylor's discovery is not isolated. Kuiper's LRDZ9 is part of a larger pattern. Webb has found dozens of supermassive black holes in the first billion years after the Big Bang. Each new discovery pushes the timeline earlier. Each new observation makes the conventional model more untenable. The universe is revealing a truth we were not prepared for. Supermassive black holes are not rare. They are not anomalies. They are everywhere in the early universe. Common, abundant, expected. That raises the most important question of all. How did they get there? Light seeds fail. Direct collapse helps but does not explain everything. Primordial black holes are exotic but increasingly plausible. Or maybe all three mechanisms operated simultaneously. Different black holes forming through different pathways, some from collapsing gas clouds, some from galaxy mergers, some from quantum fluctuations in the Big Bang itself. Webb is giving us the observations. Now theorists must catch up. They must build models that explain what we see, models that account for the masses, the timelines, the abundances, models that reconcile the impossible with the undeniable. Kuiper's LRDZ9 is the oldest confirmed supermassive black hole, but it will not hold that record for long. Webb keeps observing. The data keeps flowing. And somewhere in that data, hidden in the noise, there might be an even older monster. A black hole from the first 400 million years, the first 300 million, maybe even earlier. This is about as far back as you can practically go, Taylor said. But practical limits are not physical limits. Webb is pushing the boundaries. And the boundaries are pushing back. But the telescope found something else. Not just isolated black holes. Not just solitary monsters. It found them colliding, merging. Two supermassive black holes locked in a death spiral at the dawn of time. July 2024. Webb detected something unprecedented. Two supermassive black holes locked in a gravitational embrace, spiraling toward each other, destined to collide. And the system existed 740 million years after the Big Bang. This was the most distant black hole merger ever observed. A cosmic collision at the edge of time. The system is called ZS7. It sits in the early universe, an era when galaxies were just beginning to take shape, an era when structure was forming, an era that should be too young for supermassive black holes to exist, much less merge. But there they were, two monsters orbiting each other, getting closer with every pass. One black hole weighs 50 million solar masses. The other is slightly smaller. Together, they form a binary system, a gravitational dance that has been playing out for millions of years. But the dance is ending. The two black holes are spiraling inward, losing orbital energy to gravitational waves. Slowly, inexorably, they will collide, and when they do, the universe will shake. Gravitational waves are ripples in space-time. Einstein predicted them in 1915. We detected them for the first time in 2015. Two stellar mass black holes colliding. The merger released more energy in a fraction of a second than all the stars in the observable universe combined. But that was nothing compared to what ZS7 will produce. When two supermassive black holes merge, the gravitational waves are catastrophic. They stretch and compress space itself. They propagate outward at the speed of light. They carry information about the masses, the spins, the orbital dynamics of the colliding objects, and they are detectable across billions of light years The JWST merger already happened, 740 million years after the Big Bang. The gravitational waves are traveling through the universe right now. In a few million years, they will reach Earth, and our detectors will hear them. But the important question is not when they will merge. It is how they got so massive in the first place, 740 million years after the Big Bang. Both black holes already weigh tens of millions of solar masses. The timeline is impossible. Even starting from heavy seeds, even assuming direct collapse, the growth rate is extreme. These black holes fed voraciously, continuously, at or beyond the Eddington limit, for hundreds of millions of years without pause. Or they were born massive, primordial black holes, formed in the Big Bang, already supermassive when the first stars ignited. That would solve the timeline problem. It would explain why they are so large so early, and it would make JWST even more extraordinary. Not a merger of black holes that grew from stars, but a merger of relics from the birth of the universe itself. The discovery of JWST was announced by the European Space Agency. Webb's observations were unambiguous. Two distinct sources of X-ray emission. Two compact objects, both showing spectroscopic signatures of active accretion, both surrounded by gas disks glowing in infrared, and both orbiting a common center of mass. This was not a projection effect, not two objects at different distances that happened to line up in the sky. These were two black holes gravitationally bound to each other, a true binary. Astronomers had predicted that black hole mergers should be common in the early universe. Galaxies were colliding frequently. When galaxies merge, their central black holes eventually sink to the center of the merged system. Dynamical friction drags them inward. They form a binary. Over time, the binary tightens. The orbital separation decreases. Eventually, they merge. But predicting mergers and observing them are two different things. Finding JWST required incredible luck and incredible precision. Webb had to be pointed at exactly the right patch of sky. The spectroscopy had to be sensitive enough to resolve two separate sources. The X-ray data from Chandra had to confirm active accretion in both objects. Everything had to align. And it did. The implications are profound. If supermassive black holes were already merging at cosmic dawn, they must have been common. You cannot have mergers without a large population. JWST is not a fluke. It is representative. There are hundreds, maybe thousands of similar systems scattered throughout the early universe. Webb found one, but many more are out there, waiting to be discovered, and mergers accelerate growth. Every collision doubles the mass. A 50 million solar mass black hole merges with another 50 million solar mass black hole. You get a 100 million solar mass black hole. That black hole feeds for a few hundred million years. It doubles again. 200 million solar masses. Another merger. 400 million. Within a billion years, you have built the billion solar mass monsters we see at the centers of giant galaxies today. JWST proves that this process was already underway in the cosmic dawn. Black holes were not just feeding, they were colliding, growing through both accretion and mergers. A dual growth mechanism, faster than either process alone, maybe fast enough to explain the impossible masses Webb keeps finding. But there is a wrinkle. Mergers take time. Two black holes do not collide instantly when their host galaxies merge. First, the galaxies collide. The black holes are still separated by thousands of light years. Dynamical friction pulls them inward. That takes tens of millions of years. Eventually they form a binary. Now they are separated by light years, not thousands of light years. Gravitational wave emission takes over. The binary tightens. That takes millions more years. Finally, in the last moments, they spiral together and merge. The total time from galaxy merger to black hole merger can be 100 million years, maybe more. That is a significant fraction of the age of the universe at cosmic dawn. JWST is in the late stages. The black holes are close, spiraling rapidly. They will merge soon. But for them to be at this stage 740 million years after the Big Bang, their host galaxies must have merged even earlier. Maybe 600 million years after the Big Bang, maybe 500 million. That pushes the timeline even tighter. The black holes in JWST must have been massive before the galaxy merger, tens of millions of solar masses each, formed in the first few 100 million years of the universe. Impossible by conventional models, but undeniable in Webb's data. The discovery of JWST is a smoking gun, proof that supermassive black holes were not rare anomalies in the early universe. They were common enough to merge, common enough that Webb found a merger on one of its first deep observations. The early universe was teeming with these monsters, and we are only now beginning to see them. But Webb found something even stranger. Not black holes alone, not black holes in galaxies, not even merging black holes. It found black holes inside stars, a new class of cosmic object that should not exist, an impossibility wrapped in an impossibility. October 2025. Astronomers looked at Webb's data and saw something that made no sense. A star, distant, bright, but wrong. The spectrum was wrong. The luminosity was wrong. The size was wrong. Everything about it violated what stars should look like. It was too bright for its mass, too hot for its age, too compact for its energy output. This was not a normal star. Then someone proposed the impossible. What if it is not just a star? What if there is a black hole inside it? A supermassive black hole, living inside a star, feeding on it from within, keeping the star inflated while devouring its core. A parasite and host locked in a cosmic symbiosis. They called it a black hole star. The idea sounds like science fiction. A black hole inside a star. How is that possible? Black holes consume everything. They should destroy the star instantly, rip it apart with tidal forces, shred it into an accretion disk. There should be nothing left but a glowing ring of superheated gas. No star, just a black hole. But the math says otherwise. Under very specific conditions, a black hole can exist inside a star without destroying it. The star must be enormous, thousands of times more massive than the Sun. Population 3 giants. First-generation stars made of pure hydrogen and helium, born in the early universe before heavy elements polluted the cosmos. These stars are unstable. Their cores are incredibly hot and dense, perfect conditions for black hole formation. Here is how it works. A massive star forms, thousands of solar masses. It begins fusing hydrogen in its core, but the core is so dense, so hot, that something unusual happens. A small region at the very center collapses, not the entire star, just the innermost core. A black hole forms, small at first, maybe a few hundred solar masses, but crucially, the star does not die. The outer layers keep burning. Fusion continues. Hydrogen converts to helium. Energy radiates outward. The star shines. And at its center, hidden from view, a black hole feeds. It consumes matter from the inner envelope. Gas spirals inward. The black hole grows, but it grows slowly. The accretion is gentle, controlled. The star survives. This is a black hole star, a hybrid object, part star, part black hole. It looks like a star from the outside. It emits light. It has a photosphere. But at its core lurks a monster. A supermassive black hole in embryo, growing, feeding, waiting. The theory predicts that black hole stars can live for millions of years. The star provides fuel. The black hole consumes it. A delicate balance. Eventually, the star runs out of hydrogen. Fusion stops. The outer layers can no longer support themselves against gravity. They collapse inward. The black hole consumes everything. The star disappears. And all that remains is a supermassive black hole. Born not from stellar collapse, not from gas cloud collapse, but from a slow internal consumption. A star eaten from the inside out. This mechanism solves the timeline problem. Black hole stars can form in the first few 100 million years after the Big Bang. They start as population 3 stars, giants weighing thousands of solar masses. A black hole forms at the core. Over a few million years, the black hole grows to tens of thousands of solar masses, maybe hundreds of thousands. When the star finally dies, the black hole is already massive, a heavy seed, ready to grow into a supermassive black hole through conventional accretion. It is another pathway, another mechanism for building supermassive black holes quickly. Light seeds through stellar collapse, heavy seeds through direct collapse, primordial seeds from the Big Bang, and now black hole star seeds. 4 pathways, 4 solutions to the same impossible problem. How do you build a supermassive black hole in less than 1 billion years? And Webb may have found them. Some of the little red dots show unusual properties. They are too luminous for their size, too hot for their age, too compact for their spectrum. They do not fit the profile of normal stars. They do not fit the profile of normal black holes, but they fit the predictions for black hole stars. Scientists at the Max Planck Institute analyzed the data. They modeled black hole star spectra. They compared them to Webb's observations. The match was striking, not perfect, not definitive, but close enough to be intriguing, close enough to warrant further investigation. Webb might be seeing black hole stars, hybrid objects from the cosmic dawn, stars with monsters inside. If confirmed, this would be revolutionary. Black hole stars have been theoretical since they were first proposed decades ago. No one had ever seen one. No one knew if they could really form. No one knew if they were stable. But if Webb is observing them, the theory is proven. Black hole stars are real. They exist. And they might be common in the early universe. Think of it like this. Imagine a Trojan horse, a star on the outside, shining brightly, looking harmless. But inside, hidden from view, a black hole waits, growing, feeding, preparing to emerge. That is a black hole star, a cosmic deception, a monster in disguise. The observations are still preliminary. More data is needed, more spectroscopy, more modeling. But the possibility is tantalizing. If black hole stars exist, they represent an entirely new class of cosmic object, something that should not be possible, something that violates our intuition about how stars and black holes work. And yet, there they are, staring back at us through 13 billion years of cosmic history. Webb is rewriting the textbooks. Every month brings a new discovery. Every observation reveals something impossible. Supermassive black holes that form too fast. Naked black holes with no galaxies. Merging black holes at cosmic dawn. And now, possibly, stars with black holes inside them. The universe is stranger than we imagined. More violent, more creative, more willing to violate the rules we thought were absolute. Black holes are not rare. They are not anomalies. They are fundamental. They shaped the early universe. They built the first structures. They might even be the seeds around which galaxies formed. And that realization changes everything. It rewrites the history of the universe. It overturns decades of theory. It forces us to confront a truth we were not prepared for. We do not understand the cosmos as well as we thought. But what does this mean for us? What does it mean for our place in the universe? And why should we care about black holes that formed 13 billion years ago? Everything is connected. Black holes in the early universe are not isolated curiosities. They are not random anomalies scattered through cosmic history. They are foundational. They shaped everything that came after. The galaxies we see today, the stars we observe, the planets we discover, even us. All of it traces back to those first supermassive black holes at cosmic dawn. The old story was simple. Stars formed first. They clustered into galaxies. Black holes appeared later, growing slowly at galactic centers. Passengers in the cosmic journey. Consequences of stellar evolution. That was the narrative. That was what every textbook taught. It was wrong. Webb revealed the truth. Black holes came first. Before large galaxies, before most stars, before the universe had time to build them through conventional means. They were not passengers. They were architects. They shaped the cosmos. They built the structures we see today. Here is how it changes everything. A supermassive black hole forms in the early universe, maybe through direct collapse, maybe as a primordial relic from the Big Bang, maybe inside a black hole star. The mechanism does not matter. What matters is the result. A massive black hole, millions of solar masses, sitting in a sea of primordial gas. Gravity takes over. The black hole pulls on everything around it. Gas clouds accelerate toward it. They fall into orbit. They form a disk. The disk heats up. It radiates energy. That energy ionizes the surrounding gas. It triggers star formation. Stars ignite around the black hole. More stars form. A galaxy is born. The black hole did not form inside the galaxy. The galaxy formed around the black hole. That is the inversion. That is the paradigm shift. Black holes are not products of galactic evolution. Galaxies are products of black hole gravity. This explains why every large galaxy has a supermassive black hole at its center. It is not coincidence. It is causation. The black hole was there first. The galaxy assembled around it. The black hole is not the passenger. It is the driver. And it explains the scaling relations astronomers have observed for decades. The mass of a galaxy's central black hole correlates with the mass of the galaxy's bulge. Bigger galaxies have bigger black holes, perfectly proportional. Why? Because the black hole set the scale. It determined how much gas could fall inward, how much could form stars. The galaxy grew as large as the black hole allowed, not the other way around. The implications cascade outward. If primordial black holes formed in the Big Bang, they are the first structures in the universe. Period. Nothing predates them. They existed before stars, before atoms, before light itself could travel freely through space. They are fossils from the first microseconds of existence. And if they are common, they solve the dark matter problem. Dark matter makes up 85% of the matter in the universe. We have searched for dark matter particles for decades. We have found nothing. But what if dark matter is not particles? What if it is black holes? Primordial black holes scattered throughout space, too small to see individually, too numerous to ignore collectively. Their gravity holds galaxies together. Their mass curves space-time. They are the invisible scaffolding on which the visible universe is built. That would be the most profound discovery in a century. Dark matter identified, not as exotic subatomic particles, but as gravitational relics from the Big Bang. Black holes older than stars, older than galaxies, older than everything except space-time itself. But there is more. The mergers Webb detected prove that black holes were colliding at cosmic dawn. Every merger releases gravitational waves, ripples in space-time. Those waves propagate through the universe. They interact with matter. They carry energy. In the early universe, when everything was closer together, gravitational wave backgrounds were intense. They might have influenced structure formation. They might have seeded the density fluctuations that became galaxies. We are only beginning to understand this. Gravitational wave astronomy is in its infancy. We have detected stellar mass black hole mergers. We have detected neutron star collisions. But we have not yet detected supermassive black hole mergers. The waves are too long. Our detectors are too small, but future observatories will hear them. Pulsar timing arrays, space-based detectors, LISA. These instruments will listen to the gravitational wave symphony from the cosmic dawn, and they will reveal how black holes shape the universe through their collisions. The first 500 million years of cosmic history are being rewritten. We thought it was the Dark Ages, a period when nothing happened, the universe cooling, gas spreading out, waiting for the first stars to ignite. But Webb proved that wrong. The early universe was not dark, it was not quiet, it was violent, it was active. Supermassive black holes were forming, feeding, merging, shaping the cosmos. Every assumption we made about the early universe is under scrutiny. The timeline of star formation, the timeline of galaxy formation, the abundance of heavy elements, the distribution of matter, all of it is being questioned. All of it is being revised. And it forces us to confront an uncomfortable truth. Our models were wrong, not slightly wrong, not off by a small factor, fundamentally wrong. We missed entire formation mechanisms. We underestimated the importance of black holes. We thought they were footnotes in the story of the universe. But they are the prologue. They are the opening chapter. Everything else follows from them. This is humbling. Science progresses by being wrong, by making predictions, by testing them against observations, by revising when the data demands it. Webb demanded a revision. It showed us supermassive black holes that had no time to exist. It forced us to invent new mechanisms. Heavy seeds, primordial origins, black hole stars. Ideas that were theoretical speculation are now observational necessities. The universe is teaching us. It is showing us how little we understand, how much we have yet to learn. The James Webb Space Telescope is barely 3 years old. It has decades of operation ahead of it. More observations, more discoveries, more impossibilities waiting to be revealed. And each discovery will reshape our understanding. Each observation will rewrite the textbooks. We are living through a golden age of cosmology, a revolution in our understanding of the universe. Future generations will look back at this moment as the time when everything changed. But the deepest question remains. Not how these black holes formed, not when they appeared, not what they mean for cosmic evolution, but what they mean for us. What does it mean to be human in a universe shaped by monsters we are only now discovering? What does it mean that the cosmos is stranger, more violent, more creative than we ever imagined? That question takes us beyond science, beyond data, beyond observations. It takes us to philosophy, to meaning, to our place in the grand cosmic story. We are standing at the edge of the abyss, staring into the cosmic darkness, and the darkness is staring back. Supermassive black holes, born in the first moments of the universe, older than stars, older than galaxies, monsters that shaped everything we see, everything we are, and we are only now discovering them. There is something profound in this, something that transcends the science. We are made of atoms forged in stars, carbon, oxygen, nitrogen, iron. Every element heavier than hydrogen came from stellar furnaces. Stars lived, stars died, and their ashes became us. We are stardust. That is what Carl Sagan taught us. That is what every astronomy student learns. But the story goes deeper. Before there were stars, there were black holes. Before there were galaxies, there were black holes. Before the universe had time to build complex structures, black holes existed. They came first. They shaped the cosmos. They determined where galaxies would form, where stars would ignite, where planets would coalesce, where life would emerge. We owe our existence to black holes, not metaphorically, literally. If supermassive black holes had not formed at cosmic dawn, galaxies would have evolved differently, maybe not at all. The Milky Way exists because a black hole was there first. Our sun orbits in this galaxy because that black hole's gravity organized the structure. Earth exists because the sun formed in this location. Life arose because Earth was here. We are here because black holes shaped the universe 13 billion years ago. That is humbling. We spend our lives worried about small things, daily concerns, immediate problems, but we are participants in a story that began with monsters forming in the cosmic dawn. We are connected to the deepest mysteries of existence. We are products of a universe that is stranger and more violent than we ever imagined. The black holes Webb found are not separate from us. They are part of our origin story. The same physical laws that created them created us. The same quantum fluctuations that might have seeded primordial black holes in the Big Bang also seeded the density variations that became galaxies. The same gravitational forces that pulled gas into black holes pulled gas into stars. The same violent processes that built supermassive black holes through mergers also built large galaxies through collisions. We are not observers of cosmic evolution. We are products of it. And here is the deepest truth. We are the universe trying to understand itself. Atoms arranged in such a way that they can contemplate their own existence. Matter organized into consciousness. The cosmos looking back at its own history. For 13.8 billion years, the universe evolved. Black holes formed, galaxies assembled, stars ignited, planets coalesced, life emerged, intelligence developed, and now, a handful of conscious beings on a small planet, orbiting an ordinary star in an ordinary galaxy, are using telescopes to look back at the beginning, to see the black holes that started it all, to understand how they formed, to piece together the story of cosmic origins. That is extraordinary. The universe created observers. It created us, and it gave us the capacity to understand it. We can see across 13 billion years. We can measure the mass of black holes at cosmic dawn. We can detect gravitational waves from mergers that happened before the Earth existed. We can propose theories about the first microseconds of the Big Bang, and we can test those theories against observations. That is the gift of consciousness. That is the power of science. But with understanding comes responsibility. We know now that the universe is more fragile than we thought, more contingent. If the conditions in the early universe had been slightly different, supermassive black holes might not have formed. If black holes had not formed, galaxies might not have assembled. If galaxies had not assembled, stars might not have ignited in the right places. If stars had not formed where they did, we would not be here. The chain of causation is long, it is delicate, and it all traces back to those first black holes. We are improbable. Life is improbable. Intelligence is improbable. Everything had to go right for us to exist, and it did. Against all odds, the universe produced observers. It produced us. The James Webb Space Telescope is our eye on the cosmos, a machine built by humans to see what human eyes cannot, to peer back to the edge of time, to find the impossible, to reveal the monsters lurking at cosmic dawn. And every image it sends back, every spectrum it captures, every discovery it makes, is a reminder that we are part of something vast, something ancient, something beautiful and terrifying. The supermassive black holes Webb found had no time to exist. By every calculation, they were impossible. But they are real, they are there, and they are teaching us that the universe does not care about our expectations. It does not conform to our theories. It simply is. Our job is not to dictate what the cosmos should be. Our job is to observe what it is, to listen to what it is telling us, to revise our understanding when the data demands it. That is science. That is discovery. That is the human project. We build telescopes. We point them at the sky. We gather photons that have traveled for billions of years. We analyze them. We interpret them. We build models. We test them. We fail. We learn. We try again. Slowly, painfully, gloriously, we piece together the story of the universe. And the story is this. The universe began in violence. It was born in fire and chaos. In the first moments, black holes formed, some from quantum fluctuations, some from collapsing gas clouds, some from stars that cannibalized themselves from within. These black holes shaped everything that followed. They built galaxies. They organized matter. They created the conditions for stars, for planets, for life, for us. We are children of black holes, descendants of cosmic monsters, born from violence, forged in chaos. And now we stand here, conscious and aware, looking back at our origins, trying to understand the forces that made us, trying to comprehend the incomprehensible. The James Webb Space Telescope showed us black holes that should not exist. And in doing so, it showed us something deeper. It showed us that the universe is endlessly creative, endlessly surprising, endlessly mysterious. No matter how much we learn, there is always more. No matter how far we see, there is always farther. No matter how much we understand, there is always deeper mystery waiting to be uncovered. That is not a cause for despair. It is a cause for wonder. We live in a universe that can surprise us, a cosmos that can challenge us, a reality that demands our best thinking, our finest instruments, our deepest curiosity. We are the universe becoming aware of itself, and we have only just begun to understand what we are. 13 billion years ago, in the cosmic dawn, supermassive black holes formed. They had no time to exist, but they existed anyway. They defied the odds. They broke the rules, and they changed everything, just like we are doing now, defying expectations, breaking boundaries, discovering the impossible. We are the universe looking back at itself, and what we see